Once again, welcome to chemistry classes by Vijay Kumar Sethi, class 11th chemistry. We were discussing unit 11, the p block elements, and in this video we will discuss about chemical properties of group 14 elements. First of all, oxidation states and trends in chemical reactivity of group 14 elements. The common oxidation states exhibited by these elements are +4 and +2. Carbon also exhibits negative oxidation states. Since the sum of the first 4 ionization enthalpies is very high, compounds in +4 oxidation state are generally covalent in nature. In heavier members, the tendency to show +2 oxidation state increases in the sequence germanium, tin and lead. It means in the lead, the +2 oxidation state is most stable. It is due to the inability of NH2 electrons of valency shell to participate in bonding, and that is also known as inert pair effect. Carbon and silicon mostly shows +4 oxidation state. Ge forms stable compounds in +4 state and only few compounds in +2 state. Tin forms compounds in both oxidation state. Sn in +2 state is a reducing agent. Lead compounds in +2 state are stable and in +4 state are strong oxidizing agents because from +4 they easily convert into the +2. Okay, this is decrease in oxidation number, that is called reduction, and the species which undergo reduction is called oxidizing agent. So lead compound in +4 are strong oxidizing agents. In tetravalent state, the number of electrons around the central atom in a molecule, for example carbon in CCl4 is 8, that is octet is completed. So these are electron precise. Being electron precise molecules, they are normally not expected to act as electron acceptor or electron donor species. Although carbon cannot exceed its covalency more than 4, other elements of the group can do so. It is because of the presence of d orbital in them. Carbon does not contain d orbitals. Due to this, their halide undergo hydrolysis and have tendency to form complexes by accepting electron pairs from donor species. For example, the species like SiF62-, GeCl62-, SNOH62- exit, where the hybridization of the central atom is sp3d2. Now, reactivity towards oxygen. All members, when heated in oxygen, form oxides. There are mainly two types of oxides, monoxide and dioxide of formula MO and MO2 respectively. For example, carbon monoxide CO and carbon dioxide CO2. SiO only exists at high temperature. Oxides in higher oxidation states of elements are generally more acidic than those in lower oxidation states. The dioxides CO2, SiO2 and GeO2 are acidic, whereas SnO2 and PbO2 are amphoteric in nature. Among monoxides, CO is neutral, GeO is distinctly acidic, whereas SnO and PbO are amphoteric. Now, there is one question, problem 11.5. Select the members of group 14 that forms the most acidic oxide. Okay, answer is carbon. That is, carbon dioxide is most acidic oxide among the oxides of group 14 elements. It's commonly found in +2 oxidation state, that is lead. Now, in the group, stability of +2 oxidation state is increases due to the inert pair effect. Used as semiconductor, answer is silicon and germanium. Reactivity towards water. Carbon, silicon and germanium are not affected by water. Tin decomposes steam to form dioxide and dihydrogen gas. Reaction is Sn plus water when heated, that is in the form of steam, SnO2 plus 2H2. Lead is unaffected by water, probably because of a protective oxide film formation. Now, reactivity towards halogen. These elements can form halides of formula MX2 and MX4, where X, F, Cl, Br and I. Except carbon, all other members react directly with halogen under suitable condition to make halides. Most of the MX4 are covalent in nature. The central metal atom in these halides undergoes sp3 hybridization and the molecule is tetrahedral in shape. Exceptions are SnF4 and PbF4, which are ionic in nature. PbI4 does not exist because PbI bond initially formed during the reaction does not release enough energy to unpair 6 s2 electrons and excite one of them to higher orbital to have 4 unpaired electrons around lead atom. Simply we can say due to the inert pair effect. Okay, this PbI4 does not exist. Heavier members Ge to Pb are able to make halides of formula MX2. Stability of dihalides increases down the group. So, GeX4 is more stable than GeX2, whereas PbX2 is more stable than PbX4. Except CCl4, other tetrachlorides are easily hydrolyzed by water because the central atom can accommodate the lone pair of electrons from oxygen atom of water molecule in d orbital. Actually, this carbon CCl4 does not undergo hydrolysis because carbon does not contain d orbitals, while other tetrahalides contains the vacant d orbital, and these vacant d orbital can accept a lone pair of electron from oxygen of water molecule, so can be hydrolyzed easily. Hydrolysis can be understood by taking the example of SiCl4. It undergoes hydrolysis by initially accepting lone pair of electrons from water molecule in d orbitals of Si, finally leading to the formation of SiOH4 as shown below. See, this is SiCl4. First of all, lone pair of electron from oxygen of water donated to this silicon in the empty d orbital of silicon. Okay, first of all, this bond is made. Then HCl is removed. So, we will get this one. Now, in the same way, these remaining chlorine atoms are replaced by the OH. Okay, or finally, we will get this one. SiOH4, this is known as silicic acid. Now, problem 11.6. SiF62- is known, whereas SiCl62- not give possible reasons. Solution is, the main reason are 6 large chloride ions cannot be accommodated around Si4+ due to limitation of its size. And second one is, interaction between lone pair of chloride ion and Si4+ is not very strong. Now, important trends and anomalous behavior of carbon. Carbon differs from rest of the members of its group. It is due to its smaller size, higher electronegativity, higher ionization enthalpy, and unavailability of d orbitals. Carbon has maximum covalency to 4, whereas other members can expand their covalency due to the presence of d orbitals in other members. Carbon also has unique ability to form p-pi multiple bonds with itself and with other atoms of small size and high electronegativity. Few examples of multiple bonding. Multiple bonding means double bond and triple bond. Okay, see, carbon-carbon double bond, carbon-carbon triple bond, carbon-oxygen double bond, carbon sulfur double bond, carbon nitrogen triple bond. Heavier elements do not form p-pi bonds because their atomic orbitals are too large and diffuse to have effective overlapping due to the larger size. Overlapping is not, sidewise overlapping is not effective to form p-pi bonds. Carbon atoms have the tendency to link with one another through covalent bonds to form chains and rings, and this property is called catenation. This is because carbon-carbon single bonds are very strong. Down the group, the size increases and electronegativity decreases, and thereby tendency to show catenation decreases. The order of catenation is in carbon, this is most, then it is decreases to silicon, then germanium, and tin. Germanium and tin have almost same. Lead does not show catenation. Due to property of catenation and p-pi bond formation, carbon is able to show allotropic forms. Okay, thank you. Subscribe my channel to get the next video from this chapter. In the next video, we'll discuss about the allotropic forms of carbon.